So what I like to do is to just share some experience of a system we've developed 5 years ago called Waterman, water management system, and it is a real-time water quality forecast and management system for the smart green cities of tomorrow. So my background is in environmental hydraulics and water quality modeling, and I've been working at this for the past 35 years or so. And originally, I wanted to say just what this system is about. It provides daily beach water quality forecasts. It actually provides red tide forecasts as well, challenging as it may seem. And it's used in fisheries management. Now, the background of this is actually in the 80s when we were watching the ocean and wonder why sometimes these fish kills occur and sometimes they don't under apparently the same conditions. And we thought there must be a way of doing better in at least interpreting the data. Very often when an environmental disaster occurs, you don't know what really doesn't have a clue of what's happening, even interpreting the data. And very often socially, it's a very shocking event, very often environmental disasters. So when we started, this is not about an agency, it's just about maybe 20, 30 researchers working closely with the government, different government departments to produce a system that we believe actually works and actually produces benefits for society. So in this system, we call Waterman, there's a beach water quality forecasting system, there's a fisheries management and red tide forecast system, and embedded within it is actually a 3D EIA system, which kind of is the core engine of it all. And the project is supported by the Hong Kong Jockey Club, about 30 million Hong Kong dollar sum, and it's developed since about 2008, and it's still ongoing now, supported by different funds. And it's a collaboration between engineers, biologists, and computer scientists. And I think the most important thing is it has the deep collaboration of government departments, namely the Agriculture and Fisheries Department, the Drainage Services Department, the EPD, Environmental Protection Department, the Observatory, and then the Leisure and Cultural Services Department. So it is because you need the data, you need the interpretation, and so on. So I'll just highlight maybe at the outset some of the unique features in Asia. I think other than of course, population growth and urbanization increases the vulnerability of coastal cities. But aside from the technical aspects, which you all know, I think one or two characteristics of Asian megacities is that usually you find pollution sources very close to the sensitive receivers. And that poses particular technical challenges for models because your model has to work on a multi-scale domain in order to induce the kind of credibility and confidence by the users and the society at large. And secondly is water quality data, as much as we would like to think otherwise, are typically actually very sparse and costly. Unlike big data, the syndrome, the kind of phenomenon we have. And I think of E. coli data, bacteria data. We would like genomics would one day solve the problem of not having to wait 24 hours, 48 hours. But today, as I know it, it's still not on. I mean, it's still typically water quality data is sparse and costly. So just very quickly, Hong Kong is a special administrative region of China, about 7 million population, sitting at the edge of the Pearl River estuary, a partially mixed estuary, and next to the largest manufacturing base in the world, and is actually not a drought area. It's about 2,000 millimeter annual rainfall, and Hong Kong, as many of you would know, is a very compact megacity, if you like, very small place, 1,000 square kilometers, but within this stretch of about 1,800 square kilometers of coastal waters, actually, there's a lot of things happening. And we are bound by very, very rigorous EIA regulations, and hence the need for quantitative environmental management. I'd like to talk about two systems, not so much the technical details, but how we actually use it. So one is what interested us. Well, beaches, we have 41 gazetted beaches with lifesavers, lifeguards. And every year we have 10 million visitors, 41 beaches. And that's a very important resource to us, natural resource. Those of you who think of Hong Kong as shopping paradise, but it's really, really a lot of it's a quality of life for the average citizen is actually pretty good. You don't have to spend a lot of money just visiting these beaches. And based on epidemiological studies, we kind of grade our beaches according to E. coli. Okay, you can debate on whether it's reasonable, but as of this moment, we still rest based on E. coli. And we have 4 beach gradings depending on the concentration of E. coli, which is you can sample on any given day on a beach. And it's good, fair, poor, very poor. So good is less than 24 counts per 100 milliliter, and very poor is above 610. And if you get a very poor grading several times in a row, according to the law, you can close the beaches. Okay, so it's sampled roughly on weekly, during the bathing season, weekly intervals. And based on these data, you make your decisions. And even at this moment, it's purely based on past data, the geometric mean of the past 5 sampling. So it doesn't have any forecastability. Now, the other, when we think of water quality or management and integrated environmental management for megacity, coastal megacity like Hong Kong, in Hong Kong in particular, it's very influenced by major sewage strategy, major sewage treatment schemes. And in Hong Kong, the sewage of a population of 3 million it goes through this, what we call a harbor area treatment scheme, which is essentially goes through deep tunnels and then centrally collected in a treatment plant which provides chemically assisted, chemically enhanced primary treatment. So it's 3 million people, okay, 1.8 million cubic meter per day of sewage coming out. And and we've provided disinfection because without disinfection, you are not going to protect the beaches since March 2010, about 4 years ago. So essentially, we provide advanced primary treatment. It removes a good portion of the organic suspended solids and so on, a little bit of the nutrients. And about only 50% of the E. coli, as you know, this kind of treatment is not very effective in removing the bacteria. But we started to provide disinfection, which takes it down by 2 orders of magnitude about 3 or 4 years ago. The point I want to make here is that in megacities like Hong Kong, I mean, these are beaches. You know, the beaches are very close to discharges. I don't have a pointer here, but you see I just use the, I hope the cursor is, you see this heads L4, this L4 is really the treated sewage of a population of 3 million will come out into the harbor and in very close proximity to beaches. And there are multiple uses, not just recreation. You have fish culture zones, mariculture, you have flushing water intakes, you have monitoring stations, etc. So it is. I'm just trying to. So you have these beaches. You have fish culture zones. You have flushing water intakes. You have what we call secondary water contact areas, and we have a lot of monitoring stations. So normally in Asian cities, you have a lot of multiple uses for in a very, very compact environment, and that's why you need a. So in a way, if you think of an environment like this, you have all the non-point source, point source going in, I would say all as shear flows, as buoyant shear flows, jets of all kinds. And then it's, it can be dense jets, it can be sediment jets, it can be, and it is a multi-scale problem, ranging from the order of minutes when it comes to surface or is trapped in a certain layer, to hours or length scale of tens of kilometers before it reaches a beach. And so it's really actually a multi-scale problem. And the way we do it with forecast system like this is really we have to use a subgrid scale model rather than CFD in the near field, and coupled with a special dynamic coupling method with just a standard shallow water circulation code and with, if needed, particle tracking. So the idea of our system is something like this. So for beach water forecasting, we use a combination of data-driven models, which is derived based on a lot of research on physically based hydrological models and hydrodynamic models, field studies and laboratory studies on E. coli decay, etc., as well as deterministic models and past data. So in a way, you try to data assimilate and predict the beach water quality on every day, 11 o'clock, and then we're not aiming at the exact number, but rather at the beach grading, which is what the legal standard is. Now this is all, and through a lot of analysis, these are the main factors from solar radiation to rainfall to tide level, etc., salinity, and every beach is different. Every beach has its own model, whether it's neural network or multiple linear square. But for certain types of models, you have to go to 3D deterministic model because the environmental conditions just change. In many cities, it just change over time. And this is an example where it's very complicated terrain, where you have the major sources very close to the beaches, very complex, and then every beach is, you have all these beaches next to the urban environment. And so, for example, you introduce disinfection, it will change the entire landscape, and you cannot use data-driven models. And for those, we have to use deterministic models. And this is, for details, you can refer to the paper, but this is the whole grid for the Pearl River Delta. We have our own way of dynamic coupling, which we call a distributed entrainment sink approach. So we have a model we call JAG-LAG, a robust Lagrangian model, and we have a way of coupling at grid cell level, at grid cell level. So to do this, this kind of, and giving you data kind of forecast for every day. So I just want to, but basically we've used, this is actually put to use. We found use of this kind of system in many ways. Namely, definition of mixing zones. We spent many years just trying to grapple how to define a mixing zone. Daily beach water forecasts, setting of standards, emergency response, and also optimal disinfection dosage control, because it turns out in our setting, it's very much related to the tide. And so every day for the past 4 years, we've been providing this beach grading forecast with an accuracy of, depending on the district, ranging from very high success to around 70% success. So this has been validated against extensive data and extensive research. So this is the first thing. Now, if I could just spend 3 minutes and just talk about the other, which we take pride in, a value of the system is in fisheries management. Through this, we are able to define the carrying capacity of 26 fish culture zones in Hong Kong. So namely, how much fish can it take in what season? And we also have a red tide early warning system. And so it's based on dissolved oxygen, nitrogen, chlorophyll, and these parameters which we are. So this is an example where we say for 26 of these fish culture zones, in tons of fish, how much fish can these zones take? And whether it's overcapacity, undercapacity, identification of new zones. And this is one of the things we do, which enables you a rational basis to issue new licenses or expansion of overloaded zones by doing something, etc. So this is one thing. Now, the thing we take most pride in is actually the red tide forecasting, which we went away from fully 3D integrated models in this case. Rather, we rely on insights derived from 3D models. And so to us, to be able to forecast the likelihood of a red tide in Hong Kong, there are only two factors that counts. One is what we call a stability risk factor, which if you can simulate tides and stratification, you can produce that. We have a framework to do that. The other is nutrient threshold. And based on these and based on existing data, we can forecast the threshold, the risk, the likelihood of a bloom risk occurring, okay? And this is just, let's say, for example, of a likelihood event that actually occurred at the border near Shenzhen. So this is to just wrap up the conclusions. So from where we stand, we don't represent any agency, but we work very closely with departments, government departments. The integrated hydrodynamic and water quality forecast systems can be very useful for environmental management. And our system has been developed based on extensive validation against field data. And we believe it captures the daily water quality variations much more accurately and reliably than the current system, which would provide better protection to public health. Now, whether it has been adopted, I can report that the system has, well, you saw at the outset there are several government departments, but the degrees of adoption is entirely different for different reasons. One is there's a natural resistance to innovation, institutional resistance to innovation, but in this case, it has been positively adopted by the Drainage Service Department and the AFCD. So I think it has its successes, and we'll talk about some of the not so successes. Thank you.